All right. Last time I had stopped with the question of what are the atoms of downset of P. Just recall, P is a poset, a downset. This means that and this is a complete, this is a lattice, has joins and meets. This is the smallest downset and P itself is the largest downset. And finally, what is an atom? Atom of a poset with a smallest element is an element A of the poset, or let me say, okay, T of the poset such that x less than or equal to T implies that either x is 0 or x is equal to T. So that means the picture is something like this. You have the smallest element and you have the atom, and there is nothing in between. So there's only T is larger and there can be nothing in between. So now the question, so if we look into this situation about our poset P, I don't know how its structure looks like, but it seems that our downset has something nice. It has the smallest element, the largest element. And the question is when at all, if at all, there can be an atom. So what would be an atom? Recall also over here that we proved that if A is a member of downset, then A is actually a join of the principal downsets. Let me not write A, I was writing A for an atom. The principal downsets where this was the set of all y in P, so that y is less than or equal to x. So observe, this is always non-empty. This is the principal downset. Why? This is the smallest downset. Containing x. Now, there were some attempts, I saw it, but let's suppose, let's look into, suppose we have an atom over here. Suppose A is an atom. So A is an atom. So it's a downset. Then what happens if I have an A in A? If I have an A in A, then this picture tells me that the principal downset containing small a is a subset of A. But A is an atom, so it forces that either this is the empty or this is equal to this. But this one is not possible, as we know. This one is not possible. So this is the same thing as okay. So whenever I have an element in this atom, its principal downset is all of it. So this is equal. Now, what happens if I have this is equal to this? Well, then it tells me that A, which belongs to this, it also belongs to downset of B. So it implies A is less than or equal to B. Interchanging A and B, I can also therefore get B is less than or equal to A. So therefore, this implies that A is equal to B. So therefore, this tells me that A is a singleton, and so I'm just skipping a step over here. A is a singleton, and is downset of 0. So I leave it. It's a trivial check, but you should do this check. So it means that this lattice A will have an atom if and only if this is the only possible choice. So this is the picture of downset of P. The picture of P will have to be this. If A is an atom, then P must have a smallest element. This is equivalent. So you see, looking into downsets, we can actually start to conclude about some properties of P by looking into this downsets. We will see more of this now. So as I was explaining last time, so it seems that, so let me phrase it again. So we have so we have this map, and we know that if X is less than or equal to Y, this implies this. And obviously, in this case, we know the other side is also true. So this is saying that this is an injection, an injective order preserving map from P to downsets of P. So the picture is like this, that we started off with a P. We don't know whether it has a smallest or a largest or whatever. We somehow embed this P into a larger partially ordered set, which is our down of P, and that has a smallest element and has a largest element. Everything is below P, or everything is above this. And observe, let me draw this a little better. I don't know the situation. So the situation of P is like this. If P happens to have a smallest element, then that becomes the only thing above. There are no other things in between. Okay. So that is the scenario. So the picture is either like this, or it goes on as you can extend. But it is not only this. We have another aspect of this. So it is a kind of an injection of the partially ordered set inside this big partially ordered set, which has all possible joins and all possible meets. And furthermore, we know that every element of, or rather, let me write it over here, every downset is a join of principal downsets. So if we agree, so here is an agreement. We agree to identify an element X of P with the downset. And that is coming from this injection that we have done above. So then we can rewrite this statement as that every downset is a join of elements of P in this. So again, the situation is like this, that we take a join of elements in P. It may or may not exist in P, but if it exists in P, then it gets, then it is already there in P. If it doesn't, then that becomes an element of the extension downsets of P. So as if we are trying to fill up the gaps of these joins by putting in a dot of an element and doing it coherently, so it becomes a partially ordered set again. That means joins of bigger subsets should be placed higher up, and so on. Keeping this coherence in mind, we are just filling up those dots, those gaps of joints which were not there. But there is something more into this. It is just not an ordered set into which P is embedded in this very special way, but it is much more. So it is the best in this. So it is the best in this form. So what do I mean by this? That suppose I have a scenario like this. So I already have this. And suppose I have, let me say U. So U is a poset with joints of all subsets. So that means U has not only finite joints, but joints of all possible subsets. So we'll come to what it is. And suppose we have a function, and f is order preserved. That means x is less than or equal to y in P implies fx is less than or equal to fy. Well, if this is the scenario, then there exists a unique order preserving map. So there exists a unique order preserving map F star such that F star, so there exists a unique order preserving map F star which extends this. That means F star of a principal downset is same as this, and F star of a join of downsets is the join of the F star images. So F star preserves the joints. So it's a join preserving map. So this is, and the proof of this, I just sketched through the proof. The proof is well, B actually gives me, that is the only possible choice. So suppose I take an A. Okay. Now I know that this is actually but this is actually the join, right? So this is actually the join of these principal downsets. And then what do I do? If I have to have a function like this, there is only one possible choice that I should make, is I define it as this. Now this is well defined. Fs is a member of U and such joints exist. So this makes the definition proper. And then it is immediate to check so which I leave it for you to complete. Okay. So given any poset, we can extend it into a larger poset which has all possible joins and all possible meets, and furthermore, it is the smallest, it is the best in this way. So whenever I have any, so this is another way of saying it is the smallest, although it says much more. So whenever I have an order preserving map going into any poset with arbitrary joins, then that map extends to all of downsets. Now, another aspect over here is that I wanted to, want to draw your attention to is note the similarity over here, with especially with respect to atoms and this generation. And before I give a definition, observe that this one, the smallest, the principal downset, is the smallest downset containing X. Well, we are in a poset, so we should be speaking about the smallest downset containing X, containing an element. On the other hand, if we were in sets, we would be thinking of the smallest set containing an element. But then we know that smallest set is an atom. But here it is no more an atom. Here it is something else, right? But there is at least one similarity. The smallest set, those atoms, in the case of a set, generated every set by unions. So every set is a join of singletons. So similarly over here, every downset is a join of these. So there are so you see there is a parallel, although in one case, in the case of sets, they are atoms. Over here, they are not atoms. Okay, and the existence of an atom in downset of P is very restrictive, and if and only, and that is also completely characterized by this. So these are not atoms, right? So we could give them a name, possibly. Let's call them generators. So the principal downsets generate all the other downsets. Okay. So this situation that we observed over here, where we are saying that every element of the downset is a join of elements of P, we would like to give this feature a name. So here is a definition. a subset of a poset is said to be dense if each is a join of a set of elements of T. That is, for any there is a say a Tx such that okay, so it's a join of these elements. So in this terminology, we can say, therefore, that P is dense okay. So P is densely embedded inside downsets of P, and with this property which says that downsets of P is the smallest, the best poset with all joints. So that is one. We can. So we started with a meet. So now let's say lattice. This is a poset P in which every finite set has a join and a meet. So that means, and a lattice, a complete lattice, this is a poset in which every subset, here it was every finite subset, every subset has a join. Okay. So again, coming back over here, it says, therefore, every poset is densely embedded inside inside the complete lattice of its downsets. So that is the full story. So every poset, so let me write it over here. Every poset is densely embedded inside the complete lattice of its downsets. Now, there are, the first thing is some connections or remarks. So remarks. The first remark is about the connection with the monoids. Recall your meat semilattice. This was nothing else but commutative idempotent monoids. And what was the connection? So if you had your meat semilattice, means this was your infimum of this set AB. Well, this was taken to this ordered pair, this binary operation, and that gave the empty set. One was the infimum of the empty set, and that gave you the, and on the other hand, if you had let me say it like this, if you had a binary operation which was commutative with an identity which is E, and so it is commutative and associative, and which is idempotent, then you would define your A and B. So you define the order. A is less than or equal to B if A is equal to AB. But this equation would define it, and the rest would say that therefore from here the infimum of AB would be AB, and so on, and that would give rise to this. And therefore you can see that order preserving maps which preserve these finite meats this corresponds to just maps which preserve the binary operation. Now, obviously, there is nothing special about meat. The same could be done for joints. So either meat semilattices or joint semilattices, they are nothing else but commutative idempotent monoids. Good. But then, suppose I have the extra condition that the meat and the joint, that means the infimum and the supremum of finite sets exist. So suppose I say this. This is there, and as well as this is there. So given any two elements A and B, I have their infimum and I have their supremum. Okay, so this diamond is always there. So observe. So therefore, A and A or B is equal to A, and this is same as A or A and B. Okay, so that's exactly saying this. A and A or B, well, that has to be A, and A or A and B, that has to be A. So this gives these two equations actually give a kind of a handshaking. So why am I saying so? Because the operation of infimum gives rise to a monoid operation. This is one monoid operation. The operation of supremum gives rise to another monoid operation. So now the same set P has two operations with which they make commutative idempotent monoids. And this equation, often called the absorptive law, is a handshaking between these two operations, right? It's a handshaking between these two operations. So a set with two binary operations with respect to which, with two binary operations, both the binary operations have identities, both the binary operations are associative and commutative, and they satisfying these absorptive laws is the actual intent of this definition of a lattice. Okay. Now, in this case, so this suggests that possibly, well, we can have a set with several binary operations, right? But one has to be careful. The handshaking of these two operations should not be too much. Yeah. And well, I just make a mention. I'll give a detailed proof next time, but I make this. There can be two binary operations on a set as above, but the amount of handshaking needs to be restricted. Why? It is called the, so here is the general theorem. It is called the Ekman-Hilton principle. If are two binary operations on a set with identities say, let me write this as 1 with this for and 1 with a star for this, such that the equation holds for every A, B, C, D, and X, then A star B is equal to A equals to B. The identities, so that means the binary operations are same, the identities are therefore same, and is a commutative. So attempt to prove this, and what does star say about this handshake? You can see it says, it gives a condition, something about how these two things would match or whatever. So there is something. So that's why I said that two binary operations, if they have to maintain their distinction, the kind of handshaking between them needs to be restricted. So, and that we achieve over here. Okay. So a lattice is then just a couple. It's a pair of, coming back, it's a pair of commutative, it's a pair of monoid operations, idempotent commutative monoid operations satisfying the absorptive law. Okay? That's the first thing to be mentioned about this definition of a lattice. The second thing that I wanted to mention is obviously the opposite. So suppose if P is a poset, its dual poset is, let me write it in another color. Its dual poset is P op, here is say its operation is its relation is given by this. To denote this, we would actually write this as something like this. So what I mean is, if I write this is the same thing as saying so if you consider this as a relation, then you see the meaning. This is a subset of P cross P as a relation, and the opposite relation of this less than or equal to is this. Yeah. So that's exactly and that is also a partially ordered relation. So that also makes it a poset. So examples, you think of the real line with the usual less than or equal to. Now, if you swap, so that means if you put a mirror at 0, what you get, so you reflect, what you get is the R of, that means with the greater than or equal to as the relation, right? So the more negative numbers in R of become smaller numbers. Yeah, so just things get reversed. So over here, the notion of an upper bound gets presented over here. So the upper bound, whatever upper bound is here, that gets dualized to the notion of a lower bound. Similarly, an upper bound over here is nothing else but a lower bound here. Then the sup over here is nothing else but the inf over here, and correspondingly. All right. So, okay, another thing, what are downsets? Downsets of P. So let's see what would be the downsets of P of. So it's a downset of P of. So that means it's a subset of P such that X is implies X is in A. So now coming back to the usual order, this means X is greater than or equal to Y implies X is in A. So the natural thing to say of here is upset. So this is the downset of P of is now observe that X is this of Y if and only if the downset of X is less than or equal to downset of, remember this is an op, so let me indicate this over here. This is an op. But then by dualizing, this should become the other way round, right? Okay, so let's see. So over here, so it says, where is it? Yeah. So this is same thing as saying now let's see what is this. This is Y in, okay, Z in P such that Z is smaller than X, which is therefore Z in P says that Z is greater than or equal to X. So which we would denote as this, right? So this becomes, this is the smallest upset containing X. Okay, so therefore, it turns out that the downsets of P op is the same thing as upsets of P, but the ordered relation seems to be just reversed. So we write this as with the, so bigger upsets would be considered as smaller in downsets of P. Okay. So with then, once we have this setup, then it turns out that, recall the scenario over here. So let me now write this as, so this one would become but I know that this is equal to up of, this is the opposite of up of P. This is this. So this whole picture therefore translates to this picture. Okay. And then, so now how do you, so I leave it to you. How does the remaining picture about dense embedding translate to? So that's the question. Okay.